This lesson is about complex numbers being expressed in polar and rectangular form. You may want to watch a previous video called Complex Numbers 101 to get a more basic understanding of what a complex number is. But in summary, a complex number is a real number plus an imaginary number. And we know that complex numbers can be thought of as points on a graph corresponding to the real part and the imaginary term in the complex number. We can also consider them as ordered pairs, as the point on the graph. Whenever we know the x and the y coordinates of complex numbers, we say that those complex numbers are expressed in rectangular or Cartesian form. But there's another way to express the location of a complex number. What if we knew that we had a point or a complex number, and all we knew about it was how far it was from the origin and its angle, expressed in radians, 0.98. We could express that complex number as an ordered pair, where the distance, or modulus, was the first coordinate, and the angle was the second coordinate. When a point or a complex number is expressed that way, we say that it's in polar or trigonometric form. Another thing that you'll see in polar or trigonometric form expression is this weird thing right here. It essentially conveys the same information but in a slightly more complicated way. And as we develop our understanding of complex numbers, this notation will make more sense to you as we go. Summarizing, if you have a point in the plane, which can be thought of as a complex number, we could express it in rectangular or Cartesian form as long as we know its x and y coordinates, in which case we can express it as a coordinate or a complex number. But if we want to express it in polar or trigonometric form, we need to know its distance from the origin and its angle, in which case we can express it as a coordinate or this strange complex number notation. One very important skill is being able to convert back and forth between one format and another. Let's look first at converting a rectangular complex number into a polar complex number. I'm essentially given an x-coordinate here of -4, which I'll mark here, and a y-coordinate of 4 radical 3, which, by the way, is about 6.9. So for proper scaling purposes, I'll mark that about there. And if I want to express this complex number, which is represented by this point, in polar form, I'm going to need to know its distance from the origin and its angle. To find the distance, we could simply use the Pythagorean theorem by realizing that we know these lengths because of the way this complex number was expressed. Setting up the Pythagorean theorem and doing a little bit of algebra will eventually get me the value of r. And what I now know is that this point, or complex number, is 8 spaces away from the origin. In other words, r equals 8. Now, in order to find theta, it might be easier if we found this angle first, call it beta. If I can find beta, then I can find theta, and beta is easier to find because it's inside of a triangle with known lengths. So I can set up an equation to find beta, just like you would in normal basic trigonometry. And using basic trigonometry, I found out that beta is pi over 3 radians, or 60 degrees. But theta is going to be 180 minus beta, or pi minus beta in radians. So I now know what theta is. And now that I know r and theta, in other words, now that I know how far this complex number is from the origin, and now that I know its angle, or argument, I can simply express it as a coordinate, or in polar trigonometric form this way, both of which convey the same information. Let's look at this same problem another way. Some students would prefer to convert from polar to rectangular to polar form by using formulas instead of having to rely on a picture. Now, to convert to polar form, we're essentially converting our given x and y coordinates into r and theta coordinates. And to do that, there's two formulas that we'll see in this portion of the video, one of which essentially comes from the Pythagorean theorem. And plugging in the given x and y coordinates of this complex number and doing some arithmetic will give us our r value. The second equation used for converting between polar and rectangular is this. And because I've been given my x and y coordinates, I can use basic trigonometry to find theta. One thing you may recall is that to solve for theta in this problem, we need to convert the equation into an inverse tangent. But another complicated matter you may recall is that this conversion doesn't work in all quadrants. We're okay in quadrant 1, but in quadrant 2 we have to add pi to this result to find theta. In quadrant 3 we have to subtract pi, and in quadrant 4 we're okay as well. And I've summarized those ideas in this diagram. Because we know that our point is in quadrant 2, I'm going to add pi, figure out the inverse tangent of negative radical 3, combine terms to find out that theta is 2 pi over 3. And now that we know r and theta, we can express them in either as a coordinate or in polar trigonometric form. And this shows how we can use these equations to do the conversion without necessarily drawing a picture. Now let's look at a conversion in the other direction, polar to rectangular. Here's a complex number, or a polar coordinate. Let's see where this is on a graph. They've given us an angle, or an argument, of 5 pi over 4, which brings us around to here, and they've told us that our complex number or point is 6 spaces away from the origin, which brings us out to right here. So now we know where this complex number is, but in order to convert it to rectangular form, we're going to need to know the x and y coordinates. One way to go about this is to realize that this is a 45-degree angle based on our knowledge of basic trigonometry. And once you've realized that, you can set up an equation to solve for x and an equation to solve for y, and do the basic algebra using your knowledge of what the cosine of 45 and the sine of 45 are. And using some basic algebra and arithmetic, you'll solve for x and y. And once we've found the x and y coordinates, can put this in rectangular form. Notice I've made my x and y coordinate negative because we're in quadrant 3, so clearly that's the case. Here's a better way to express the same thing. A different way you could have approached this problem is to take your polar coordinates and immediately express them as a polar trigonometric number, and then, using your knowledge of what the cosine of 5 pi over 4 is and the sine of 5 pi over 4, you could have arrived at this result in a quicker and more expeditious way.